Okay, there's a wrinkle. I wish it were this simple all the time. There's a wrinkle. And I'm going to illustrate that with this example. It turns out that you can make music, sort of, by clamping a hacksaw blade to a post and then twanging it. Okay, twang, twang, twang. It's country and western. Okay? Now, if I draw a graph showing the two lowest harmonics that can occur on the hacksaw blade and find the wavelength of each harmonic, I do that by drawing pictures. Well, there's a hacksaw blade. Where it's clamped to the post has to be a node. And this end over here is free, so that's got to be an antinode. Now, it turns out that that makes this fundamentally different from this case. In this case, I was going from a node to a node. The two ends were the same. If I go from a node to an antinode, the longest wave that will fit is only half a football. Now, this is important. When the ends are the same, I start with one whole football. When I go to the next allowed resonance, I've got to add a football. So I go from 1 to 2, I double the number of footballs. Let's look what happens here. First of all, the fundamental wavelength is not 2L. It's not twice the length of the system. In this case, I've only got half a football. It takes 2 footballs to make a wavelength. I've only got a fourth of a wavelength. That means a wavelength has to be 4L, not 2L, 4L. Now, we still call that the fundamental because it's the lowest frequency that will resonate. But if I go to the next allowed resonance, I still have to have a node there and an antinode there. When I go to the next highest resonance, the next higher resonance, I always add a football. So watch what happens. How many footballs do I have?
1.5.
1.5. Now another way of saying that is 3 half footballs. I went from a half football to 3 half footballs. I tripled the number of footballs that fit in the system. That means my footballs have to get smaller by a factor of 3. What that means from the wave equation is that I'm going to have a frequency that is now 3 times the fundamental. Now, what I'm saying is that there's 2 distinctly different types of standing waves. When the ends are the same, you go from 1 football to 2 footballs to 3 footballs to 4 footballs. And likewise, you go from F1 to F2 to F3 to F4. When the ends are different, when one's a node and one's an antinode, you go from half a football to 3 half footballs. The next one would be 5 half footballs. And what we see is that we go right from F1 to F3 to F5. The even harmonics are missing. Okay, so in summary, when the ends are the same, I get all of them. F1, F2, F3, F4, F5, F6. When the ends are different, one a node, one an antinode, you just get the odd ones. 1, 3, 5, 7, 9. Okay. Check to see if your neighbor's on the bus, please. In this problem, we take a string, thank you. We take a string and we hook it to a post with a frictionless, massless ring. Ooh, does that ring any bells? Does that sound familiar? This is going to be a fixed end or a free end? Free end. It's a free end. Then we let that string wrap around a pulley and it's attached to this heavy mass. Now that mass holds that string so it's right there next to the pulley all the time. Can't move. So is that going to be a node or an antinode? No. It's going to be a node. This is a free end. It's going to be an antinode. And so this is a case like the hacksaw blade. Now we find that you can set up standing waves by just jiggling this block. Now the mass of the block is chosen to determine the frequencies at which this will oscillate. If I look at the wave equation, V is equal to F lambda, the tension in the string is what's going to cause the V. Okay? And so I find that certain frequencies at which I jiggle this block are going to set up the standing waves on that portion of the string. Now the question we want to ask or answer is which frequencies are going to make those standing waves. Now let's do this problem together. We've got 3 minutes. I'll do it quickly. We're asked to find the tension in the string. Can you do that in the head?
Yeah.
Yeah, that tension is going to be 300 newtons. And you get that from a free body diagram. The weight is 300 newtons. And I need to do that. Thank you. And the tension is going to equal the weight, also 300 newtons. Is that better? Now the wave speed is given by the square root of the tension over the mass density. Well, that's going to be the square root of 300 over, well, let's see, what would that be? The mass density is the total mass of the string divided by the total length of the string. Oops. I was never here. Okay. Now, that's going to be 0.01 kilograms over 3 meters. Now, I can also multiply top and bottom by 100 and say that's 1 over 300 kilograms per meter. And I do it that way because when I put it in here, I can invert and multiply, and now I'm taking the square root of 300 squared. I can do that in my head. That's going to be 300 meters per second. Now you can see that I cooked these numbers so they'd work out easy. Unfortunately, I cooked them to the point where it looks like there's something important there. I get 300 for both answers. That's just because of the way I chose my numbers. There's no physics there, okay? They just happen to be the same. Now, the first harmonic is going to go straight from a note to an antinote. The next harmonic is going to add one football. So this would be the first harmonic, and this would be the third harmonic. Now, to find the frequency of this harmonic, I need to know what the wavelength is. And then I can find with V is equal to frequency times wavelength, I can find that frequency. Well, I can find the wavelength by using the number of footballs times lambda over 2 is equal to the length of this part of the string that's oscillating. That's 2 meters. So I'm going to have 3 half footballs times lambda over 2 is equal to 2 meters, or lambda 3 is equal to 8 meters over 3. So I come over here and I put in 300 meters per second for the speed. I put 8/3 meters for the wavelength, and I solve for F3. We're out of time, people. I'm sorry to keep you extra. I will not charge you for that extra minute. It's free. It's on me.